Alright, so in this presentation I'm gonna talk about using LSTM neural networks to predict daily stock returns. And you can think of LSTMs as a way of computing something for now. And if you don't know what a stock return is, it's basically the change of a stock's price. So if the return is positive, the price has gone up, and if it's negative, the price has gone down. So to tell you a bit more about LSTMs, they are a type of neural network, and neural networks have the ability to learn patterns and recreate them on their own. They can learn to compute things simply by looking at data. So they don't need to be hard-coded by a programmer to give a somewhat correct answer to a question. Furthermore, what makes LSTMs special is that they have the ability to remember the past. They have this sort of internal memory, and this makes them suitable for time series prediction. A time series is essentially a sequence of data ordered by time, as seen in the graphic here, and time series prediction is when you attempt to predict the next item in line. And this property of LSTMs made me wonder whether they can predict the future return of a stock, the next day, for example. And after doing some research, it turned out to be quite a challenge, because if you look at the stock market as a system, it turns out to be a shockingly chaotic one. So there are thousands of individuals trying to buy and sell stocks any second. It's just a mess all of it, and this has resulted in a few schools of thought. And the first one is those that believe in the so-called random walk hypothesis. It simply states that stocks behave in a totally random manner, so you can't predict it at all. And then there are those who believe in the efficient market hypothesis. And it's simply that you can't beat the market. If people could predict the price of a stock tomorrow, it would be reflected in the price today, as the same people would buy or sell in anticipation today. It's kind of like the observer effect. Observing something changes it. But I couldn't just take these hypotheses at face value and just believe that it's impossible to do any kind of prediction. So I wanted an answer to this question. Can models trained by LSTMs predict returns more accurately than two sort of benchmark prediction methods that I had selected? And those benchmark methods were, first off, the random prediction method. And let's say you have a dataset that looks like the one displayed under the title here. You have 50% of the samples being a negative return of a stock, and 50% of the samples being a positive return. Say you were to flip a coin and predict a negative return if you get heads, and a positive return if you get tails. With this dataset you would end up eventually with about a 50% accuracy. So because of this, we can assume that with a similar looking dataset as this one, if our models perform as good or worse than the random prediction method, it's not really that great, because our own models are much more complex and it takes a lot of time to train them. And if they aren't better than just flipping a coin, it's not worth our time. That's a way to know whether our models are any good at predicting stuff. And then there is the one-sided prediction method. And say you have a dataset that looks like the one displayed under that title, where 90% of the samples are a positive return. If you were to predict a positive return all the time, without even looking at the stock itself or the trading data behind it, you would end up with about a 90% accuracy. Even though the method itself is kinda stupid and there is no logic behind the predictions. So we can say that if our dataset looks something like this, and our models don't perform better than the one-sided prediction method, there's not really a point in using it, because you could just assume that all samples are of one type or the other and get a higher accuracy. So after coming up with these benchmark predictions to measure our models against, I just got to work and collected a ton of data. So I collected up to 10 years of trading data for 60 stocks. Half of them were from the US and half of them were from Sweden, and all of them were highly traded. And then I went ahead and trained the LSTM neural network I had created on predicting positive or negative returns using this data. And then I went ahead and tested the accuracy of the models generated by the LSTM neural network on data it had not seen during the training. So you might be interested in the results by now. And before telling you the accuracy of our models, I just want to go ahead and mention something else that came up during the execution of this. And it's in fact the distribution of our dataset. So it turned out that 52% of all samples across all stocks had a positive return, and 48 had a negative return. It's quite an even distribution, and it's almost 50-50. And this means that if you were to use the random prediction method, you would end up with an almost 50% accuracy. And if you were to use a one-sided prediction method and just say that all days are positive, you get a positive return every day, you would end up with about a 52% accuracy. This means that for our models to be any better than this one, or the random prediction method, we would need to have an accuracy of over 52%. So that's the question. Did our models live up to this standard? And it turned out that, in fact, it didn't. The mean accuracy for both US and Swedish stocks was about 50%. So it was not better in any way. And this led me to conclude that the models we trained with our LSTMs don't seem to work very well with highly traded stocks in the US and Sweden. But then, of course, there is room for improvements in the future. So, for example, I believe that if you were to lower the time frame of your prediction, so instead of predicting the return for the next day, you were to predict it for the next 15 minutes, it's likely that you would see a somewhat higher accuracy. But before parting ways, I just want to share some lessons I learned during the execution of this project. And the first one is to not jump to a conclusion too quickly, because a lot of the time you really need to think about whether the results you see can be generalizable to another population or another instance in time or another situation. And the second lesson is that the hardest problems are usually the most interesting, at least in my opinion. So why bother doing something if it's so easy to get an answer? Why not spend your effort on something that's really a mystery? At this point, I just want to thank you for listening, and I wish you a nice day.